Hello, I'm Rafael Schaefer, and in this part of the tutorial, I talk about joint communication, identification, and sending. Let me start with a brief motivation on the topic of joint communication and sending, which is sometimes also named integrated sending and communication, and a briefly refers to the problem where we want to communicate and sense jointly using the same resources. And it is expected that this facilitates a seamless integration of physical and digital worlds. It will enable a network to automatically react to changing environments. It will save energy in an Internet of Things network, and it is expected to stimulate a wide range of future communication systems. So let me introduce the particular model that we are interested in here. In this setup, basically, we were looking at a transmitter that wants to transmit a message W over a channel P, YZ given XS, to a receiver which tries to decode the transmitted message W. At the same time, as we are looking at a joint communication and sending setup, we want to try to sense or to estimate the channel, to learn something about the channel we are communicating over with. So, and therefore, the channel is modeled as follows. So it is a probability distribution with an input X that is the code word that we are transmitting. And at the same time, the channel is governed by a state S, which is according to a certain state probability distribution PS. And that channel outputs a channel output Y, which goes to the receiver. And at the same time, we're considering some kind of feedback in the sense that a feedback Z is available at the transmitter on which the state that governs the transmission is estimated. So these are the two tasks here. So we have a communication task. We want to transmit the message W from the transmitter to the receiver. And at the same time, we want to try to estimate the state that governs the transmission. And this is how we want to model the joint communication and sending problem. Yeah, and a brief motivation or where this all comes from is basically that we want to use a radar and communication system at the same time using the same resources or the same bandwidth of the channel. So to state some basic results, let me briefly introduce some concepts here. As I said before, we want to sense the channel state that governs the transmission, and the quality of the sensing operation will be measured by the expected distortion that we experience, right? So if you look at here, Sn, that is the actual channel state that governs the transmission. S hat, that is our estimate of that channel. And this is given in a per letter description here. With this, we can then define what we call achievable. So to be more precise, we call a rate distortion pair RD achievable if we find a code with the two following properties. On the one hand, the probability of error should go to 0, right? So if the block length n goes to infinity, the probability that the receiver incorrectly decodes the message that has been sent should approach 0. And at the same time, the distortion on our estimation should be below a target distortion D. Right? So once these two criteria are met, we call a rate distortion pair RD achievable. From this then follows the capacity distortion trade-off C of D, which is basically simply defined as the supremum of R such that RD is achievable, meaning that I'm fixing a distortion threshold D that I want to ensure, and then the capacity is basically the maximum achievable rate such that the distortion measure is satisfied. So having introduced this, we can state the capacity distortion trade-off for this particular channel. As we are looking at a state-dependent memoryless channel, the capacity distortion trade-off is given by this expression here. So C of D is the maximum mutual information between X and Y given the state S. So this maximization here is done over all input distributions Px that further satisfies the distortion requirement D. Yeah, and this is basically the main result if you look at this particular joint communication and sending setup from an information theoretic perspective. And if we look further into this particular expression here, the capacity distortion trade-off being maximum IXY given S, we see that it kind of recovers the capacity in the unconstrained case, right? So in the case of unconstrained distortion, meaning that basically we do not impose any constraint on the distortion here, it becomes the maximum over all input distributions Px, mutual information XY given S. So now we want to make use of these results and these insights to look at the joint identification and sensing setup, right? So what we've heard before, we heard a lot of things about the identification framework, and now we want to combine this with the sensing operation, with the additional sensing that we just have introduced, right? And so the system model looks quite similar. Again, we have a transmitter, a sender here. We want to send a particular message, I, and therefore we encode that message. It goes through a state-dependent channel, here a DMC that also depends on the state S. So we have a channel output YT. It goes to a receiver who tries to decode that message. As we are now in the identification setup, the decoding process is not recovering the precise message, but it is now answering the question if the transmitted if the transmitted message is some I prime of interest, or is it not, right? So this is the regular or usual task for identification. Also here in that setup, we have a feedback link, which models the sensing operation, right? So we have some feedback from the channel. And with this, we are trying to estimate the state of the channel, right? It goes to an estimator. So we want to estimate the channel S hat in this case here. But we can do a little bit more, right? So we have learned that in the identification case, feedback really helps the transmission, right? And therefore, we do not only use the feedback, so the output of the channel, to estimate the state, but we want to also use that feedback for the encoding process itself, right? Because we have learned feedback can help, can improve the identification, right? And therefore, we want to make use of the feedback for the identification capacity here, right? This is the main motivation here. This is a crucial thing that we want to ensure, right? And therefore, we basically take the system model that we've just seen for the communication part, and now we try to obtain similar things for the identification case here. And similar, we will need to define a certain distortion function, right, that measures the quality of the sensing operation again. And this is again, modeled quite similarly as before. So the average distortion, d bar, is again a per letter distortion between the true state and the estimated state, where we are conditioning of a particular code word here, right? And with this, we can also define the minimal distortion function for each input symbol X, right? So D star, this is now the minimal distortion function for a given input signal X here. And this is basically, we are just looking for the minimum here of H, which are all these functions here, right? These estimation functions that take X and Y to, estimate S hat. And so we are looking for each particular situation, for each channel input, we are looking for the minimal, or for that function that gives us the minimal distortion here, right? And this is called D star in the following. Having said this, we can move on, and I can also define the term of achievability. And in this case, we say that an identification rate distortion pair RD for that channel WS is said to be achievable if for every lambda there exists an n null such that we find a sequence of identification codes. In this case, we are considering deterministic identification codes, while ensuring that the average distortion is satisfied, meaning that the average distortion d bar is below the distortion requirement capital D. Right, and then similarly as before, we can define the deterministic identification capacity distortion function CD of D, and which is again the supremum of R such that RD is achievable. Right, similarly as before, we are giving us a distortion constraint or requirement D, and then we're looking for the maximum rate that is achievable under this constraint here. And this leads basically to the following result. It is a lower bound or an achievability bound for the ID capacity distortion function. So let's look into that. The deterministic ID capacity distortion function of the state-dependent channel is in the super exponential codebook size of 2 to the 2 to the nr, right? So we have again this double exponential scale here, and that one is lower bounded by this expression here, right? So we're maximizing over the input symbols, and then we have an entropy term here, right? And these input symbols are all x, such that the minimal distortion here, D star, that we've introduced, meets the distortion requirement, right? So this basically restricts us the set over which we look for the maximizing input symbols. Yeah. So this is the main result here, and here we really see that feedback really helps, right? And what we further can comment is that if we do not use the sensing result for communication, that we then have the deterministic identification capacity in the codebook size of 2nr. So here we do not have a double exponential scale, but only a regular or a single exponential scale. And this is max PS of the entropy of X. Okay, so let me wrap up this part here. So what have we done? So what have we looked at? So basically, we started with a joint communication and sensing problem. We stated some results for that. And then we extended that one to the identification case, where we jointly identified a message and sensed the state of the channel. So a joint identification and sending setup. And here we have seen that the sending data really helps for the deterministic identification, as it increases the number of identities from exponential to double exponential. So this is quite remarkable, right? So we really have an exponential gain here. And this, let me conclude here by saying that this is just the beginning, right? So there are many future directions that you can look at. So far we only have a lower bound for the ID capacity, right? So it was an achievability. Now an upper bound would also be nice, like a converse result. Let's see how tight we are, or if we can even improve our achievability bound. We only looked at the discrete memory channels. So what happens in Gaussian channels? So this is something one should consider. Or maybe we can also go beyond point-to-point channels, right? So looking at other models where we have identification. Another problem that I also want to discuss here is the problem of security in ISAC, in joint communication and sending, right? I mean, by definition, from the problem setup, I'm using some signals in two ways. I want to communicate, and I will also want to use this signal to simultaneously sense something, right? So whatever I'm doing, I use the same signal to simultaneously achieve reliable communication and some target sensing, right? So my channel output feedback, which may be given due to reflections, for example, is used both. I want to learn the channel parameters, and I also want to improve the communication performance here. However, if I'm using a single channel for both tasks, for communication and sending, this may leak or may cause information leakage about the transmitted message to the two potential eavesdroppers, right? Which might even be the sense target. Yeah. So think of the following setup. I want to communicate to a certain receiver, and at the same time, I want to use this signal to sense potential other users in the area. If that signal contains some confidential information, right, it is very likely, or I have to be prepared to, that this communication signal with the confidential information may also leak information about it to potential eavesdroppers around, right? Because I'm actively also designing that signal to sense other users. Yeah. And obviously, as we have sensing and the secrecy, performance are measured with respect to the signal I'm using at the sense target, right? There must be a trade-off. And this is something that we want to look at here. Yeah. So what have we done as a small teaser? So basically we have inner and outer bounds on the secrecy distortion region of a partial secrecy scenario, strong secrecy constraint, and perfect output feedback. So in general, these bounds are loose. So we have inner and outer bounds. But for particular realizations of degraded and reversely degraded channel models, we even get the exact rate regions, right? So that we are able to establish some kind of capacity here. Yeah. In the general case, we have partial secrecy, meaning that we only want to protect a certain fraction of the message. We can also specialize this to the case where the entire message should be kept secret. If you look at the papers, we also have binary examples that illustrate these methods, and it shows that they outperform separation-based secure communication and state sending methods. And we can also evaluate that for some additive Gaussian noise scenarios. But let us look more into detail here, and let us start with a precise problem formulation that we are interested in. As usual, we have some kind of transmitter, right? So we have a message M that is split up into two parts, M1, M2. As we will see, that will be for the partial secret case, but that message goes to an encoder. It takes the message and some channel feedback that we've received before. So it encodes it into a code word or code symbol XI, which goes through a channel. And this is now a broadcast channel because we have two receivers. We have the legitimate receiver, which tries to decode that message. And at the same time, as we're considering a wireless medium, it may be overheard by a non-legitimate receiver, an eavesdropper somewhere else, who may also overhear something of our communication. As before, we have a state-dependent channel, meaning that now we have two states because we have two receivers. The legitimate receiver has a state S1. The eavesdropper may observe a state S2. And we have a certain channel feedback due to the sensing operation. And this is, again, used twofold. So we're using that, of course, to estimate the channel state as hat. And at the same time, we also may use that for the encoding process itself, right? Because we know that once we go to secrecy or secure communication, feedback also may help here. So I think I already said many things here. This is the encoding process, right? So we have the transmitted message M. We have the delayed channel output feedback ZI-1, right? This is delayed from the previous time instant. And we're encoding these two into a code word X here. The receiver observes its own channel output Y1 and the state S1. And of course, it tries to decode the message M hat, right? So it tries to decode or to recover both parts M1 and M2. The eavesdropper, on the other hand, observes its own channel observation Y2, its own channel state S2. And at the transmitter side, we are trying to estimate the state sequence as hat. And this basically we're using, of course, the transmitted signal that we are aware of because we know what we transmit, and the channel feedback, Zn, and this is used to estimate the channel state. In the following, we will consider the case of perfect output feedback, right? It's some kind of idealized model here, which means that Zi minus 1 is basically just both channel outputs Y1 and Y2. As mentioned already in the beginning, we're looking at the very general case of partial secrecy, meaning that we may even be able to split the message M into two parts, M1, M2, while only M2 need to be kept secret from Eve, right? So this gives us even more freedom here. Okay, and this leads to the definition here, similarly as before, of achievability. And now we say that a secrecy distortion tuple R1, R2, D1, D2 is achievable. If there is a code, encoder, decoder, estimators, such that the following conditions are satisfied, right? So we have here the rate constraint, of course. This is the reliability that the decoded message M hat should be decoded error-free or almost error-free with high reliability. We have a strong secrecy criterion here, so the mutual information of the message M2, that is the one that we want to protect. M2 and Y2, this is the channel output at the eavesdropper given the channel state S2. That one should be small, right? So there's no or only very small leakage about the confidential message M2 to the eavesdropper via its channel output Y2. And of course, we have distortion measures D1 and D2. And as before, we consider kind of a per letter distortion metric here. And then the secrecy distortion region is the closure of set of all achievable tuples with partial secrecy and perfect output feedback, right? So we are just looking for all tuples here that satisfy these conditions here, and this gives us the whole region. Let me remark some things which are a little bit technical or useful. As always, or as before, we are using a per letter distortion metric and IID states, and this really simplifies the analysis. But you can also motivate it by saying that past observations are independent of present and future ones, so this is not made up. But at the same time, lending the transmitter to know state prediction ability to adapt its transmission on the fly. If you looked at the strong secrecy criterion, we said you have noticed that we have conditioned on the state S2, but obviously this is also equivalent to that notion here, mutual information M2 to Y2 S2, as the transmitted message is independent of the state sequence. So both definitions or versions are valid here. Okay, let us look at the results here that we have obtained. So first, we look at an inner bound, so this is an achievability scheme, which holds in general, so no conditions on the channel itself here. So the whole region includes the union over all distributions. So here we already see that we have two auxiliary random variables, U and V, forming that kind of Markov chain here. And then the region is given as follows. So R1 should be smaller than I, U, Y1, S1. So R1 is associated to the message M1. So this is the part that does not need to be kept confidential, right? So that's the open public part. And you see that the rate of that message is upper bounded by the mutual information, some kind of channel quality from you, from the transmitter to the legitimate receiver, given that state. R2, that is the part that should be kept secret. This is the upper bounded or by the minimum of R2 prime and this part here. And here you can see that this is kind of a reliability constraint here. We have V to Y1, right? This is again the channel quality of the legitimate receiver minus R2, R1. This is the part that has been already used for M1. R2 prime refers to the confidential constraints here, right? So here we see as a well-known expression or structure that comes from a wiretap coding principle, right? So legitimate receiver, channel quality minus the eavesdropper penalty here. And plus we have some entropy term here, which comes basically the channel output you use can be used as some kind of secret key, which may also further increase the secret communication rate here. So this is an inner bound and achievability, which gives us something we can actually achieve in this particular model. We also have an outer bound, like in converse. And here the region is included in the union over all distributions. So we have one auxiliary random variable v only in that case here in that outer bound. And here you see similar things, right? Again, R1 is mutual information I, Y, V, Y1, S1. And R2, here we have again some kind of difference, and here these kind of reliability constraint here. Okay, having said that, I want to add that these bounds, the previous inner and outer bound, they are general in the sense that no requirements, no specifications have been made on the channel, so they can be very general. If we particularly specialize the channels, and if we look at certain special cases, then we can get even more, then we can get even tight results, right? So we have seen that the inner and outer bound, they do not match in general. But if we look at particular channels, they do match, and then we get precise capacity results here. So let us look at the degraded channels. Therefore, we say that a channel is physically degraded if the true channel has the following Markov chain structure here. So we go from the channel state S1 to X, or from X to Y1, and then from Y1 to Y2. So Y1, the legitimate receiver, is the stronger user here. Vice versa, on the other hand, the reversely physically degraded channel, the degradation order is changed, meaning that now we first go to Y2 and then to Y1. So the eavesdropper is the stronger user here, right? So we have degraded channels, we have these Markov chains, and important is that we look at both cases. On the one hand, physically degraded, the legitimate receiver is the stronger user, reversely physically degraded, the eavesdropper is the stronger user. So what do we obtain here? For the physically degraded case, we get this one here. And you see that this is exactly the region that we have seen in the outer bound, meaning that once we fix our channel to be physically degraded, we get capacity, we get a tight result in the sense that now the achievability bound simplifies and then matches the outer bound that we've seen, right? So in this case, we really get capacity. So inner and outer bound achievability and converse, they do match, and we get a precise characterization in that case here. Likewise, for reversely physically degraded channels, we also get a capacity result here. Also in this case, achievability and converse, they do match. Both results coincide, both bounds. And again, R1 is kind of the legitimate transmission bound here to the legitimate receiver. R2, again, we have these kind of constraints here. Now you see that we are losing something, and in particular, basically, we are losing the wiretap coding part, right? Because this part here, this difference, will always be zero because the eavesdropper is a stronger user, meaning that this quantity here is larger than this one, so that this guy here will always be zero. Having observed this, one can easily show that then inner and outer bound coincide again, and we get this result here for the reversely physically degraded case. Okay, let me wrap up also this part here. So what have we looked at in the second part? We looked at a secure ISAC setup, and we have seen that these methods, if we jointly define or merge the communication task and the sensing task at the physical layer, we can significantly improve the performance of what secure communication by only using wiretap codes, for example, right? So we really gain something. Due to the sending, we get some channel feedback, which can then be used as one-time pads or secret keys, which further increases our communication rate or secure communication rate. We have seen that we got the in general, we get bounds, inner bounds, outer bounds, but we have seen that for degraded cases, which includes both degraded and reversely degraded, the bounds become tight and we get a precise characterization for the capacity here. Everything has been done for partial secrecy, meaning that we've dealt with both parts of the message, a public part and a private part. And of course, we can also extend that to the full secrecy case by saying that the whole message M equals to M2 needs to be kept secret. No part is allowed to be public. And for there, we can further get some further results for particular channels, for example, binary channel coefficients and binary modulated input signals. We have further results for continuous alphabets, where we have Gaussian channels or correlated Rayleigh fast fading scenarios. For these kind of scenarios, we have further results, and I would like to refer to the corresponding papers here.
For the fifth part of this tutorial series, I'll be talking about the implementational aspects, specifically of randomized identification codes. We've previously discussed them a little bit in this tutorial series, but mainly we've also focused on deterministic randomized identification codes. I'll highlight the differences in randomized ID codes before presenting the separation approach and the tagging codes that are an explicit form of constructing these randomized ID codes, before presenting multi-tag identification and some use cases in the end. So, as we learned earlier, in identification we have two parties, Alice and Bob, and they both select a message that we also call an identity from a mutual set of identities. So in this case we have a set I of 8 identities, I1 to I8, and both of them randomly select, or maybe deterministically select, one of these messages. In this example they both select the same message. So Bob wants to learn now that Alice also selected this message, and the ground truth of this scenario is that these two identities actually match. To encode this identity, Alice then selects a random code word X from the set of all possible code words X. It does this not from the full set, but from a subset. This subset E of possible code words is associated with the identity that Alice selected. If it selects, or if she selects a different identity, then she also selects her random code word from a different subset. Note that these encoder subsets overlap already, as we learned earlier also about the decoding subsets, for example in deterministic identification. This randomly selected code word X is then transmitted over a noisy channel to the receiver or sink, Bob. Bob uses the received code word Y, which is a distorted version of the code word X selected by the encoder side, and then wants to find out whether this received code word is associated with the identity that Bob selected, right? So the identity that Bob selected is associated with a decoding subset D, I2 in this case, right? And this is a subset of the set of code words Y, of all possible receivable code words Y. And in this case, the distortion was not so bad, or in fact, there's no distortion in this example, and therefore the received code word Y actually falls into the decoding subset DI2, and therefore Bob learns, the received Y is actually part of the subset that I'm interested in, and therefore Bob verdicts that these two identities actually match, and because this is also the truth, we have a true positive result in this case. Now, of course, we can also have the issue that I said earlier, that we have this overlap, right? So when Bob selects a different identity, for example, identity 5, then the received code word Y also falls into this set of code words that are associated with an identity that is actually different from the identity that Alice has in mind. And this is a type of false positive error, because Bob thinks that these two identities match, even though they are a mismatch. So this is the false positive case. Then, of course, we also have a true negative case. So if we go back one slide, here we see Alice selected this code word, and this resulted in a bad case on the verifier side, right? But when Alice selects a different code word, right? So you see it's a different code word. Then the received code word, if the channel does not distort anything, will be outside of this decoding subset of Bob. And then we will actually find out on Bob's side that the two identities mismatch correctly. So we have the true negative case. Of course, there's also a fourth case. It's the false negative case. So going from the baseline of the true positive, when we have a distortion in the channel, it can of course also happen that the received code word lands outside of the decoding region of the verifier side. And then in that case, it's a missed identification, right? The verdict is mismatch between these two identities, even though in truth they match, and then we have a false negative error. So overall, we have 4 different possible results: true positive, true negative, false positive, and false negative. As I already highlighted, these false negative errors are a result of distortions in the channel, because a code word that should be received by the verifier or interpreted by the verifier as an indicator for matching IDs, and this is ruined essentially by the distorting channel. So the distortion creates false negatives where the code word falls outside of the corresponding decoding subset. On the false positive side, we see that these are not caused by distortions in the channel, because in fact these two transmissions here happen without errors. The channel does not distort the code word, and still there's an error, and this is caused due to the overlap in the decoding subsets, as we already learned for deterministic identification. Maybe I point out here the difference between deterministic and randomized ID codes. So as we learned in deterministic identification, this encoding function here is deterministic. So an identity is always mapped to the same code word X. So there's an X for I1 and a different X for I2 and so on. And here in randomized identification, we actually select a random code word from a set of code words, and only this set where the element is selected from is random. The overlap in these decoding sets, that is mutual for both randomized ID codes and deterministic ID codes, is then the reason for these false positive errors. They are also called type 2 errors. A good ID code, of course, tries to minimize both kinds of errors. So let's look at how to create good ID codes, right? Because we want to talk about the implementational aspects of creating these codes. So a bad ID code for the distortion kind of errors, for the false negative errors, does not help with the distortion, so it doesn't mitigate these effects of the channel. And a good ID code, of course, helps against these distortions. Codes that help against distortion are well understood. They are called forward error correction codes, right? They are known from message transmission in the Shannon picture, and we know them quite well. Also, they are not solved, but we are approaching the level where we can call them solved, because we are very close to the theoretical limits in some cases at least, right, with polar codes and LDPC codes. Now, the second kind of error, the false positive error, is caused from this overlap between the code word sets. This overlap, of course, is introduced because we want to fit more identities or messages into the same amount of code word space, right? So by allowing this overlap in the decoding regions, we actually achieve this double exponential scaling that was mentioned in the earlier parts of this tutorial series. So, of course, if we wouldn't have any overlap, we wouldn't have this kind of error, right? But then we would also be in the message transmission domain and not in the message identification domain, because in message identification we can actually accept this kind of error because it becomes very small for good codes. So in a bad ID code, we have a large overlap between code word sets, and this large overlap leads to a high false positive error probability. And for a good ID code, we limit this overlap to a hopefully small amount. This problem of creating a code that has small overlap between its decoding but also encoding subsets is colloquially called a noiseless ID code. And why that is, I'll explain you on the next slide. So because we can actually, because we know that these errors have distinct sources, we can also use distinct solutions for each of these. So we don't use a joint correction method, like it's implied here, right? So there's one encoding that creates a code word and then it is transmitted. Instead, we use a separation approach where we say first, after we selected our identity, we use a noiseless ID code that creates a code word that has little overlap with other noiseless ID code words. And only then we use forward error correction to prove this code word that we created against the distortions that happen in the channel. Because overall, and this is also what happens in modern communication systems with the abstraction layers, you see that a good forward error correction code or well-designed code that fits well for the channel that we experience, this signal processing chain actually creates a virtually error-free transmission. So we abstract on this level, right? And in that case, the code word or the noiseless ID code word that is created here can be assumed to be transmitted perfectly to the verifier side. By the way, we call the verifier or the receiver in the identification coding also the verifier, because it's not strictly a decoding of the message, but it's only verifying in a binary choice whether the received code word assumes or implies identity between the two identities or not. So to summarize, FEC codes can create virtually error-free channels or noiseless channels, and therefore we talk about noiseless ID codes on this side. The FEC code takes care of the false negative errors that could happen, and then we need to find a code that also makes sure that these false positive errors are also kept at a minimum. So this is what a noiseless ID code then looks like. So here in the middle we see we have a virtual or virtually error-free channel V instead of the noisy channel W before. And if we have this virtually error-free channel in the middle, then it actually makes sense to make the decoding subsets or verifier subsets that were called D before and the encoding subsets E that we knew before they are both now in the noiseless case, so we call them C, and they are also identical, because if we create a code word C here and we transmit it without error over here, it makes sense to have these two code word sets be identical. And this makes the problem of creating the code much easier, because we can build on existing solutions for the forward error correction codes, and we only need to find a code. We don't even need a decoding set, right? But we only need to find these kind of code word subsets from a set of code words that have minimal overlap between each other. How does this look like in practice? So this is where tagging codes come into play. They are the only known explicit way of constructing randomized ID codes using the separation approach. So here we see again the chain that we had before, right? So Alice selects an identity and then it selects or finds the code word subset of the associated identity, and then it randomly selects a code word from this set of code words. In the tagging code world, it looks like this. So we represent our identity not as a variable or an integer, but it's an array in the finite field of size q, and it's an array of length k. So here we have 5 symbols that are between 0 and 32, for example. And then this identity is encoded using, for example, a Reed-Solomon code. The reason for that I will get to in a bit, but for now let's just focus on that we encode this identity and we create a larger Reed-Solomon code word out of this, right? So here we have a length k identity, and out of that we create a length n Reed-Solomon code word. And now we use this Reed-Solomon code word as our subset of code words. And we do this by associating with each position in this code word also the position number of this code word. And this creates our code word set CA or CI2 maybe in this example. And we then will not transmit this Reed-Solomon code word because this is the message transmission domain, right? Or where we borrow these Reed-Solomon codes from, but rather what we want to do is we only select a single position in this whole code word, right? So maybe this position here, and then we transmit this tuple of the position that we randomly selected and the value of the Reed-Solomon code word at that position. This value is also called a tag, and then we have the random tag position, and the tuple of the tag position and the tag is then this noiseless ID code word C. So this again in the other picture, right? So we select our identity A or ID1, we encode it, and we get a tuple of a position and a tag value. This is then further encoded by a forward error correction code, right? And then we get our code word X here. So this is of course, like typically we talk about binary channels. Or sorry, not binary channels, discrete channels. In this example, there's also modulation, but let's just consider that it's only a discrete channel. So we have our code word C here, and our code word X is here. So the random creation of the code word X that we know from the first slides actually takes place in this encoder. And then, of course, the forward error correction encoder is deterministic, and the result X is randomized because the input to the forward error correction encoder was random because the position is randomly selected. And then this code word X is distorted by the channel and we receive a code word Y. And then the FEC decoder creates or decodes this received code word Y. And the message that is kind of part of this FEC code word that is received distortedly is then split into the position and the tag value. The position is given to the encoder of the receiver side, which then determines its own tag value of that place. So I go back a few slides, or just this slide. So as we see here. Here it looks like that we create a code word and then we have to find out why is the received code word part of our code word subset or not. And the way we do this implementationally is that we selected a random position at the encoder side, but for the decoder or verifier side, we receive the position and we use the random position that also the encoder used and check at that position in our own Reed-Solomon code word, which creates the code word set for the identity, whether these two tags actually match or not. So this is what we show here. We get the position out of the forward error correction decoder, or if you abstract this away, there's just a perfect transmission of the position and the tag value that the receiver gets as an input. The position is given to the encoder at the receiver side, which creates the tag value at this position for this identity and compares its own tag value with the tag value that it received over the virtually error-free channel. And then it's just a simple comparison. Are these two tags identical or not? In this case, they are identical, even though these two identities are different. So we got unlucky and get a false positive error. This is the same example with both code words, what they look like. So this is again the code word set that I talked about before, right? The tuples of the position and the tag value. And here we see that the two identities get these kind of Reed-Solomon code words with their positions. So this is the code word set for ID 1 and this is the code word set for ID 2. And we can see that there are some positions in which they overlap, for example, position 31 or position 1. But there are also other positions in which these Reed-Solomon code words differ. And now I can talk about the reason why we use Reed-Solomon codes. That is because Reed-Solomon codes are actually maximum distance separable codes. So they have a very high distance. And the nice thing about high distance codes is that this means that they have few positions in which they overlap between these identities. And this is exactly the property that we need for a good noiseless ID code, that it is a high distance code, because this makes the false positive error probability as small as possible, because the code cannot be have a higher distance than a maximum distance separable code. Maybe just one final thing. We can compute the false positive error probability easily when we know both Reed-Solomon code words, because we can just compute each position, or we compute both Reed-Solomon code words, and then we compare in how many positions they overlap and how many they don't overlap. And then the fraction of overlapping positions divided by the length of the full code word is then the false positive error probability of this pair of identities. Of course, there are many pairs of identities for which this exists, but this is the false positive error probability that is specific to this pair of identities. As I said before, Reed-Solomon codes are maximum separable codes, so this is nice. However, a single Reed-Solomon code is not enough to create a capacity-achieving ID code. So what we do is actually, so we saw this upper part before already with the single Reed-Solomon encoding. What Sergio Verdu and Victor Wey proposed was that we concatenate two Reed-Solomon codes, and this way they could actually show the first explicit code construction, also the first ID code that is capacity achieving in the infinite regime. So what we do is, again, we have this identity here in a finite field of size q. Then we encode it with an outer Reed-Solomon code, and then each of the symbols of this Reed-Solomon code word of the outer encoding, we first have to do a base extension, because the inner Reed-Solomon code then will also only take as input one of these symbols. So we have to create a longer input to the inner encoding, and then each of these outer symbols, after it has been extended, is then encoded by an inner Reed-Solomon code. And this way we create a very long code word, because these are just stacked together. And then we have a very long code word with a very high distance. And this is actually enough to achieve, like if the length of this code word goes to infinity, the distance between these code words will not grow as quickly, and therefore the code can actually achieve identification capacity, which is this double exponential scaling. It achieves the capacity in the double exponential scaling of these randomized ID codes. So to talk again about the false positive error probability, this is of course one of two important metrics. One important metric is how many identities or messages can we fit into this, or how many messages does this code support? And then what is the cost of having that many identities, right? Because the more identities we have, the more they overlap. I mean, this is exaggerated for visual reasons, but the more identities we have, the higher this overlap will be. And therefore we need to investigate what does this error probability actually look like, because this is what determines the performance of our system in the end. For that reason, I will just point out some elements here. So what is very important is that the error probability is always defined pairwise, as I said before. So there is a different error probability between, let's say, the set of identity 1 and 2 compared to the set between identity 2 and 6. Like in this example, 2 and 6 don't have any overlap at all, and these have an overlap of maybe 50% or something like this. So there is no global false positive error probability, but it's a property of each individual ID pair. So there's this pairwise overlap, and from the pairwise overlap of the code word sets directly follows the pairwise error probability. We have many pairs. Approximately there are exactly the cardinality of the set of identities squared pairs of identities. Of course, for the false positive error probability, the number of this reduces because, for example, in this case, we have matching IDs, right? So we have to subtract that from the number of pairs for which the false positive error probability would happen, because if the pairs match, then of course it's a true positive case, and the false positive error probability is 0 in that case. And also we have to divide, after subtracting that, the number of pairs by 2, because this is symmetrical, right? It doesn't matter if you have ID1 here and ID2 here, or ID2 here and ID1 here, the overlap is symmetrical. And then overall, we get a large number of false positive error probabilities for each of these pairs, right? And then what we need to show the capacity of this, or what information theory needs, we won't be doing this in this tutorial, is to find a bound on the overlap, or on the false error probability between these two, or all pairs of identities. And then in the proofs, we can show if the bound goes towards 0. This means that all other false positive error probabilities must also go to 0, because even the worst case goes to 0 in the infinite regime for infinite length code word sets. Now I want to point out that because I said before, we have a number of identities, and the behavior of the false error probability are metrics essentially to evaluate how well identification codes perform. I introduced you to the bound already. Another metric, so this is the worst case value for the false positive error probability. There's of course also the mean false positive error probability, which is like the mean is a typical statistical measure, right? So this is also of interest. And now what I will introduce you to is a baseline for ID codes, because we want to determine somehow what coding gain do we have. So when we do this, let me go back here, when we use this concatenation of Reed-Solomon codes, this is nice in the infinite regime because we achieve capacity on the theoretical level. But how does this translate to practical scenarios, right? Because in practice we are not in the infinite regime, and we need to know what is the benefit of using this complex concatenated Reed-Solomon encoding. Because I should point this out. Doing this encoding is computationally quite expensive, and this remains one of the larger challenges of creating explicit and practical randomized ID codes, that creating these long Reed-Solomon code words is very expensive. There are already solutions to improve this, because in the end, if we only select a single tag, so we only want to know what is the tag value at position 3 here, right, 0, 1, 2, 3, the value is 2, then we do not need to compute the full length, but we only need to compute this. So there are already methods that implement these concatenated Reed-Solomon tagging codes by not computing the full Reed-Solomon code word, but rather only going down this branch. So it would only compute this position of the outer Reed-Solomon code word and then this position of the inner Reed-Solomon code word. In this way, lots of computational complexity is saved, but still it is very expensive to do these kind of computations. And because it is so expensive to do this, we want to evaluate what is actually the gain we get for paying so much computational complexity. And for that, we proposed no code as a baseline for these ID codes. which basically means to use uncoded identities for identification. Because when we use an identity like we saw earlier already, right? So we have this array in base Q. Also here we see tags, right? So we have 5 positions here, and we can just select a random position from this identity. So we just send a random part of our message essentially, and using this we can also perform identification. This is also a simple kind of code if you want, even though it's uncoded. And any code that we use should be better than not using a code, of course, right? Because otherwise we don't have a coding gain. Because this we get for free, and for the concatenated Reed-Solomon code, for example, we need to pay lots of computational power. And then what we see, this is a schematic visualization, is that it's actually not a simple answer, what is the coding gain. So here we see in blue the no code, so this is what we get for free, and in red we get the concatenated Reed-Solomon. It's called RS2 for that reason, 2 Reed-Solomon codes we see in red. And what is plotted here is it's a histogram essentially. So on the horizontal axis we see the false positive error probability that is specific to each individual ID pair, as I explained earlier. And here we see logarithmically the number of ID pairs for which this specific false positive error probability occurs, right? So most of the ID pairs have the average or the mean error probability. And then for the Reed-Solomon code, as we learned before, we have the bound, right? It's not necessarily tight, but just for visualization reasons, we just say the bound is tight, and it's exactly where the last kind of, or the highest false positive error probability occurs. And then we see all the Reed-Solomon code word, pairs of IDs that use the Reed-Solomon code. They exhibit false positive error probabilities that are below this lambda2 bound, the lambda bound that is the bound on the false positive error probability. For the no code, we do not get such a tight bound. The bound is actually very close to 1 all the way outside of the screen, because you can imagine if you have 2 different words and you have maybe 9 zeros and a 0 in the end, and then you have 9 zeros and a 1 in the end. This is a code word that has a 10% error probability, 90% error probability, because the message differs only in a single position. And the longer the message gets, the higher potentially this overlap probability becomes. But of course, these are only very select few pairs that have this very small overlap, as you can see here. The large majority of no-code or uncoded ID pairs also have the same kind of average error probability. So if we only look at the average error probability, we actually do not have any coding gain at all, because both, like if you select the same field size for both codes, both have the same mean error probability. When we only consider the bound, which is what is typically done for information theory, then of course the uncoded approach is completely useless, because the bound is very close to 1, and therefore you will never have a very good code when you use uncoded identification. And here we again see the bad case and the good case, right? A good pair has a low error probability with little overlap, and the bad pair has a high overlap with a high error probability. And then I also want to point out the shape of these curves, because we found in simulations that the Reed-Solomon code, of course, limits or removes actually all ID pairs that have, or it doesn't remove, but it removes code word set pairs that are above this bound. But this comes also at the cost of removing code word pairs that are below a specific minimum false positive error probability. And what this leads to is that we have different percentiles, for example, that are also an indicator that no code or uncoded identification codes might be helpful in some scenarios. Because as you can see here, the 99th percentile, this is of course not exact, it's just like to visualize the point that the percentiles for the concatenated Reed-Solomon code are not necessarily better than of the no code, because as you can see here, the 99th percentile of the no code is below the one of the Reed-Solomon code, for which we have to pay lots of computational power. So the 100% percentile is of course the bound. So for that, we pay a lot of computational power. But if we loosen this restriction from 100% to 99%, or maybe to 1 minus 10 to the minus 6, it is not immediately clear that we get a benefit from these Reed-Solomon codes. Yes. So the distribution matters a lot. And then finally, I want to point out that we can compute the ratio of how many ID pairs are actually above this, which can be quite low in practice. But what I also want to point out is that the probability of selecting a pair is very important, because if we select an ID pair very often, it is very important what kind of false positive error probability it has. If all of them are selected uniformly likely, then we get this mean error probability. But if we get some skewed kind of ID distribution where a select few number of ID pairs happen a lot, then their specific false positive error probability is quite important. And in that case, the bound again helps us a lot, because it limits how bad it can actually become. If we select a very unfortunate pair of ID pairs a lot, and it has a very high false positive error probability, then we have a very bad system performance if we use uncoded ID codes. So in those kind of scenarios, Reed-Solomon codes can again shine. To come to a conclusion in a few minutes, I just want to briefly point out, in multi-tag identification, you don't only transmit a single tag, but you transmit several tags, and each additional tag, of course, reduces the error probability further. So this way you can, I will skip this for time reasons. For this reason, you have a trade-off where each additional tag that you transmit, so your number of data that you transmit increases, and the more data you send, the lower your error probability becomes. And in this case, you also deterministically exclude some pairs from further consideration. However, here again, the Reed-Solomon code has some unfortunate behavior, because it doesn't have the same minimum false positive error probability as the uncoded identification codes. So you can see here in the blue line approaches message transmission eventually in the number or in the amount of data that you have to transmit before your error probability becomes 0, whereas the Reed-Solomon code vastly exceeds the amount of information that message transmission would help. And of course, if we just transmit a message, we have 0 error probability in the false positive domain. And then in those scenarios, Reed-Solomon codes again have a few issues. Just a brief mention of use cases. In one scenario that we imagine, we have a digital twin of a robot in the cloud, and the cloud wants to help this robot with its positioning or its goals. And to reduce the amount of traffic between these two, they can first communicate whether they two think the robot is in the same position, for example. And if they have a mismatch between these two positions, they can actually update this, but only after identifying whether these two position values are identical or not. Furthermore, if we are in very noisy channels, for example, in space communication, this can be imaginable. We can increase reliability because ID codes reduce traffic so much that we free up many bits essentially that we can use as additional bits for the forward error correction. Of course, we introduce this type 2 error because of these overlaps that we have, but the reduction in type 1 errors is much larger than the increase in type 2 errors. So overall, we get a gain if we have an identification scenario in noisy channels. With this, I want to conclude this talk. Randomized ID codes can be very beneficial, as we saw here in very noisy channels. It is still subject of research whether these Reed-Solomon codes, for example, are the best way to go. There are also Reed-Muller codes that have less computational complexity than these Reed-Solomon codes. but they also have worse error behavior. But this might be a middle way between uncoded identification and these complex concatenated Reed-Solomon codes. Thank you very much for your attention.